Hello everyone. Let's analyze. So we've talked about what it means for a function to be integrable. Let's consider this function, 1 over the square root of x, integrated from 0 to 1. Now if we were to apply our definition of Riemann integration to this, we would see that by that definition, we don't have Riemann integrability as we have defined it already. And the reason is because the function is not defined at 0. And of course, the first partition would include 0. Furthermore, as x approaches 0, my function approaches infinity. Our definition of Riemann integrability cannot handle yet the infinite in this regard. However, if we were to not know that and just integrate, as we might if we were in a Calculus 1 or Calculus 2 class, we probably could show that that is in fact a number. But how do we know it is? And how do we define it if Riemann integration, as we've already defined it, does not apply? So today we're going to talk about improper integrals. As I said, we've discussed what it means for a function to be Riemann integrable. But what if the domain of f is unbounded? For example, integrating e to the negative x from 0 to infinity. Or what if f is unbounded, as in the example we just saw, the integral from 0 to 1 of 1 over the square root of x? So in both of those examples, infinity is involved. So we see infinity in the upper limit of the first integral. And in the second integral, even though we don't see explicitly an infinity, we know that as x approaches the lower limit of my integral domain, 0, my function trends towards infinity. And of course, when we see infinity, we should think limit, because essentially infinity means something that grows in an unbounded way. Now here's another question. We've considered functions that were defined over closed intervals, but what if the domain of my function is a subset of a closed interval? Well, that question we can answer straight away. If f is defined over some subset of a closed interval, then we essentially can extend the domain to the closed interval by just letting f be 0 if I'm in the closed interval but outside of a. Then if this extended function is integrable over the interval a to b, we say that the original function is integrable over the subset capital A. So let's give a definition of what it means for an integral to exist if the domain is unbounded. Right? This is one example of what we call an improper integral. So let f map a to r, and let my function be non-negative. So this is important. Right now, we're only considering the case of functions that are not negative anywhere in the domain. Again, we're going to extend our function to the entire row line by just letting the extension be 0 anytime I'm outside of the domain A. Then if the integral from negative a to a of my extension converges to a finite number and the limit as little a goes to infinity, then we say that the original function is integrable over the domain A. Furthermore, the integral over the domain A of f is equal to that limit. So again, if A is an unbounded domain, it makes sense that the integral definition should involve some limit as something trends towards infinity. Now, a bit of a warning. For this definition to apply, f must be non-negative. So, for example, the integral from negative a to a of x dx is 0 for all a. So, of course, in the limit as a goes to infinity, I would get 0. However, the integral of x over the entire line is not defined. So notice that in the definition, I'm taking the limit as a goes to infinity of a integral whose domain is symmetric around 0, the integral from negative a to a. But what if I take an integral that is not symmetric around 0? For example, the integral from negative k to k plus 1. As k goes to infinity, this integral domain still grows to cover the entire real line as k goes to infinity, but it doesn't do it in a symmetric way. If, when I take that limit as k goes to infinity, I get something finite, then can we say that the integral of f over a exists? Well, it turns out that we can. Then f is integrable if and only if, for a sequence of subsets of R, the subset sequence is growing. In other words, each new subset contains the previous. And it's growing without bound. In other words, there's no limit to how big it grows. Another way of expressing that is that for any symmetric interval around 0, negative a to a, there's a subset bk that contains it. So if the integral over bk exists and the limit as k goes to infinity, then we say that the integral of f over a exists. So now to return to the example that we looked at previously. What if my function is unbounded rather than the domain? So for example, if I want to integrate 1 over the square root of x from 0 to 1. We know that 1 over the square root of x is defined on the interval 0 to 1 but not containing 0. So let's define fm to be f of x if f is bounded by m and 0 otherwise. So we see in the magenta line, we see fm of x if m is 2. Right, so for the first chunk, when f is greater than 2, we get 0, and to the right of that, we just get the function. Now, if I let m increase and integrate fm, as m increases, if I get arbitrarily close to a number, then we would have to say that number is the integral in question. So let's define that. Let f be positive, or non-negative rather, for all x in a. If the limit as m goes to infinity of the integral of fm exists, then we say that the integral of f over a is equal to that limit. Right, so here we see that as m goes to infinity, that magenta line converges to the blue line. And if I take that limit, I'm taking the limit as m goes to infinity of 2 minus 1 over m, which converges to 2 as m goes to infinity. So therefore, the integral from 0 to 1 of 1 over the square root of x is 2. Let's take a look at another example. In this case, let's let f be 1 over the square root of the absolute value of x. And let's consider the interval from negative 1 to 1. Well, we know that the domain is actually the interval from negative 1 to 1, except for 0. So when we say the integral from negative 1 to 1 of 1 over the square root of the absolute value of x, what we actually mean is the integral over a, which is that interval from negative 1 to 1, but not containing 0. But again, we can get around that by just extending it to that interval by just letting f be 0 anywhere I'm outside of its domain. So we're going to apply our definition. We're going to let fm be f everywhere that f is less than or equal to m and 0 otherwise. and then integrate fm and take the limit as m goes to infinity. So if I integrate fm from -1 to 1, in other words, the area under that magenta line, I get 4 minus 2 over m. And if I take the limit as m goes to infinity, then that just converges to 4. Which makes sense because this function is just a reflection of the previous one over the y-axis. So, of course, our integral should be double the answer from the previous example. And we have our answer. So, we know how to define improper integrals for non-negative functions if the domain is unbounded and if the function is unbounded. But what about in general? What about when f is not always non-negative for all x in the domain? So for example, is this function integrable if a is the interval 0 to infinity? We can't apply the definitions we've looked at previously because my function is not non-negative over the domain. So what we're going to do is we're going to split f into its positive and negative parts. So we'll let f plus be, well, the positive, or rather the non-negative part. And suppose that the integral of f plus exists. We know how to analyze the integral of f plus over an unbounded domain because we've already defined that scenario. Because here f plus is non-negative by definition. And similarly, we're going to look at f negative separately. F negative is the negative part of it. In order to analyze the negative part, we're going to just flip it by multiplying by -1 so that it becomes a non-negative function. And suppose that that integral exists. Again, we have all the tools we need to understand whether that integral exists because it's a non-negative function over an unbounded domain, but we can handle that now. Well, if the integral of f plus and f minus, remember f minus is the negative part flipped to become positive, if both of those integrals exist separately, then the integral over a of the absolute value of f exists and is equal to the sum of the integrals, and the integral of f over a exists and the integral of f over a exists and is equal to the difference of those integrals. So now we have a definition for the integral of f. Now, we should perhaps be a little careful here. Notice that the integrability of f plus and f minus implies that the absolute value of f is integrable. However, we cannot just say that the absolute value of f is integrable implies that f plus and f minus exist. That's not true. Consider the function that is 1 for rational numbers and -1 for irrational numbers. Of course, we know that that's not integrable over a bounded domain. But the absolute value of that function is, because the absolute value of that function would just be 1. So it's important that we break f into its positive and negative parts and analyze them individually. Okay, so we've defined how to consider improper integrals when the domain is unbounded, when the function is unbounded, and when the function is non-negative, or if it's not always non-negative, in other words, a generic function. But aren't there any shortcuts? Aren't there any properties of my function that would save me some time? For example, does continuity buy me anything? And it does. Suppose f is defined on that unbounded domain and is continuous. Then if big F is the antiderivative of little f, then we say little f is integrable if and only if the limit as x goes to infinity of the antiderivative exists. And in that case, the integral from a to infinity of little f is, as you would think, as suggested by the fundamental theorem of calculus, the limit as x goes to infinity of the antiderivative of f of x minus f of a. So for example, e to the negative x is positive, continuous, and it has an antiderivative. If I take the limit as x goes to infinity of the antiderivative at x minus the antiderivative at 0, I would get infinity minus 1, which is 1. So in fact, that function is integrable. And we can use the antiderivative in this case to show it. So this is the unbounded domain scenario. What does continuity buy me for a bounded domain but a unbounded function? Suppose f is defined on the interval open a to closed b, and it's non-negative. Then f is integrable if and only if the limit as h goes to 0 of the integral of a plus h to b exists. Now, by the way, the integral from a plus h to b must exist because on that interval, f is continuous. So it's not a question of whether the integral exists, but rather does the limit as h goes to 0 exist? And if it exists, then we say that's the integral of f from a to b. So for example, this gives us another way of computing the integral from 0 to 1 of 1 over the square root of x. It's the limit as h goes to 0 of the integral from h to 1. So again, I can take the antiderivative, evaluate from 1 to h, and take the limit as h goes to 0. And I get 2. Of course, we knew that was coming, but we now have another way of doing it. And now we know how to integrate properly and improperly. That's it for today.